And welcome back. As we continue our cosmic journey, let's go ahead and start dating some planetary surfaces to really start figuring out the age of the cosmic bodies we're going to be looking at. So how do we determine the age of something like a planet? It's not like we have been around to see when a planet first came along. Well, the easiest way to start saying this is, well, how do we know the age of the surface we see on planets and moons? Because, we can't obviously just look at the Earth's core, but we can look at its surface. So if a world has a surface, as opposed to being mostly gas and liquid, such as Jupiter or Saturn, astronomers have developed some techniques for estimating how long ago that surface solidified. Now note that the age of the surface is not necessarily the age of the planet. And we'll talk about why that is. On geologically active objects, and here's our why, planet weathering, or vast outpourings of either molten rock or erosion from things such as wind and rain, have erased evidence of early epochs or eras in time and present us with only a relatively young surface for investigation. So, for example, on Earth, we have all these. We have, molten rock, we have erosion, and these, of course, are constantly reshaping the surface of the planet. So, let's look at a planet that might not be as geologically active, or maybe another body, such as the moon. Well, how can we determine the age? Well, the first way we can do this is starting by counting the craters. So one way to estimate the age of a surface is to count the number of impact craters. Now, this technique works because the rate at which impacts have occurred in the solar system has been roughly constant for several billion years. Yes, in the very beginning of the solar system, it might have been pretty chaotic, but eventually things stabilized, and so the rate of impacts became much more stable. Now, this technique has been applied successfully to many solid planets and moons. Astronomers can then use the number of craters on different parts of the same world to provide important clues about how regions on that world evolved. So on a given planet or moon, the more heavily cratered terrain will generally be much older because, again, remember what we talked about earlier in the history of the solar system, there were a lot more impacts. Another way we can do this is through radioactive rocks. So if we want to trace the history of a solid world, another way we can do this is by measuring the age of the individual rocks that are on its surface. Now, after samples were brought back from the moon by Apollo astronauts, one of the techniques that we have is to date these rocks. And we did this using the same techniques that we used to date rocks on Earth, and we applied it to the rock samples from the moon, and that helped us establish a geologic chronology for the moon. Scientists measured the age of rocks using the properties of natural radioactivity. Around the beginning of the 20th century, physicists began to understand that some atomic nuclei were not stable, but can split apart or decay spontaneously into smaller nuclei. Now, the process of radioactive decay involves the emission of particles, such as electrons, or of radiation in the form of gamma rays. And that's going to get us into an interesting conversation topic about half-life. Because for any one radioactive nucleus, it is not possible to predict when the decay process will happen. However, there is a specific time known as a half-life in which decay is likely to occur. A particular nucleus may last a shorter or longer time than its half-life, but in a large sample, almost exactly half the nuclei will have decayed after a time equal to one half-life. Half the remaining nuclei will have decayed to two half-lives, leaving only one half, or a quarter of the original material. So let's look at this radioactive decay with an example here. This graph is showing us the amount of radioactive sample that remains after several half-lives have passed. So you can notice we start with 1, then move to half, then a quarter, then eighth, then 16th, then 32nd. After one half-life, we of course have half the sample left. 2 half-lives, we have a quarter. 3 half-lives, we have 1/8. So the decay of radioactive elements in a rock sample is not necessarily going to cause any visible change in the appearance of the rock. Instead, what's going to happen is that material is slowly going to be replaced by the decay products. So, for example, if you have uranium, you can watch as that slowly decays down into its different elements. So that way you can then, if you know the decay process, we can then work backwards to figure out, based upon what is decayed, to see what the age of that material is. And then, of course, if we know the age of that material, we know that the body that has that material has to at least be as old as the object that has decayed.